Hey everyone, it's great to have you with us here today. I'm Brian Rogers from Intel. I'm a technical solutions architect, and we're here to talk to you about leveraging the AI reference kits for faster AI solutions that are tailored to your needs. With me today, I have Bereket Gaguro, who's a senior analyst for Accenture. What we're going to be focused on is, industry use cases for AI reference kits that we have built in collaboration with Accenture. So, hey, Barry, do you want to go into any specifics around this right now?
So I'll use this slide to kind of give you a better idea and answer that question. So, as you probably know, AI workloads continue to grow and diversify with use cases in computer vision, speech, recommender systems, and more, right? So Accenture and Intel have been working collaboratively for some time now, and in that time, Intel has been making some strategic moves to make their presence known in the AI space, from acquiring companies like Habana Labs and Converge.io to developing computer vision AI platforms for the edge. Now, what stood out to us were the One API toolkits in which Intel has developed tools that can be leveraged to optimize and deploy machine learning and deep learning models. That's why Accenture has chosen to partner with Intel to develop what's now known as the AI reference kits, which in a collaborative effort was designed not only to accelerate the adoption of AI across industries, but also to contribute to the goal of helping developers build solutions for some of the most popular AI use cases. And so these reference kits cover industries such as energy and utilities, financial services, health and life sciences, retail, and more. And there are also kits that apply across industry, including chatbots, intelligent document processing, and network intrusion. These kits were developed using Azure virtual machines with the help from components of Intel's end-to-end AI software portfolio. And the goal is that these optimized frameworks and tools will enable developers to introduce AI quickly and easily into their applications, or if they just want, they can just boost their existing AI solutions. And as of today, there are 34 ref kits available and are offered to the open source community for use and download on GitHub. So anyone who wants to can infuse AI into their solutions. Coming up next, we can dive into the hardware and software and how they play a role in the optimization. So there are two crucial parts: hardware acceleration and software optimization. And the main objective is not to only improve your performance and lower total cost of implementation, but also to achieve productivity while developing your AI solutions on any platform. For hardware acceleration, Brian, can you talk to us a little bit about this part?
Yeah, happy to. I see it's really cool in the slide that you have here is that there's two different CPUs, and it could be confusing if you don't look detailed into them, but one is our Xeon product line and the other one is also our desktop product line. So meaning that we do cover the gamut of helping our development teams get what they need in every place out there. So for our Xeon CPUs and even for several of our desktop CPUs, we have accelerators on these CPUs that really, if you're not leveraging our software and unlocking the instruction sets that are on there, say, in example, AVX512, you're really missing out on the ability to get the full value of the Intel CPU and how it can be used. Further, with the new market coming up in place for the GPUs, we're seeing great adoption there, and we have an FPGA lineup that's just definitely top of line.
Yeah, and so it's the combination of these two with hardware acceleration and software optimization that'll help you achieve the best performance for your training, inference, as well as data pre-processing workloads. And as Brian said, regardless of what devices and accelerators your systems might have, One API is the piece that's bridging all these to a common ground. And so Intel has been listening to its customers, developers, and communities, and has delivered a standardized solution for accelerated compute. Now, these One API toolkits allow you to build and optimize your AI pipeline on a variety of hardware. And that's how we leveraged Intel technologies to develop the AI reference kits, which take advantage of the software optimizations for popular frameworks such as TensorFlow, PyTorch, scikit-learn, and XGBoost. And to maximize performance for your workloads, we found that using Intel, the optimized frameworks and libraries on Intel machines help to achieve that goal. Now, we have performed testing on non-Intel hardware, and we've seen that Intel optimization works on similar architecture, And we've compared before and after optimization, and we've seen significant performance. And when we look at the performance price, we're also unleashing this new way of optimizing our workloads that helps us reduce costs, which is ultimately very important from a perspective of the business. And we'll talk more about the tools that are available to us from one API in the following slide. So just once again, we created the AI reference kits to help developers streamline and expedite the development and deployment of their AI workloads. At the bottom here, we have all the toolkits and the solutions that one API technology has to offer. And above that, we have developers who focus in different areas of the AI space. And what we essentially want is to use the reference kits to enable developers to learn how to deploy AI faster. Each reference kit includes training data, an open source trained model, libraries, user guides, and Intel AI software products. Now, we've selected several popular business use cases across multiple industries using various models. And these kits were designed to give developers a head start to solve similar business problems in their industry. And they can use the reference kits with their own data set, while we provide the source code, optimization techniques, and benchmarking results to showcase the performance difference between the unoptimized and optimized models. In the next slide, we can talk in more detail about the tools Intel provides for its developers to speed up their workloads.
And Barry, it really sounds like you've chosen to make it really seamless for developers to just come in, get started, get up and moving. So these kits are available also in an open source community, right, where they can kind of go and browse and see what's going on with them. Is that correct?
Correct. Yeah, we've designed this with ease of use in mind for our developers, and so they're open source in GitHub, and anybody can go ahead and try them out. So if I could direct your eyes to the image on the right, we have here a typical machine learning pipeline. It may vary for some, but for the sake of this example, let's assume it is. The middle section contains optimization tools that Intel provides for accelerating your machine learning and deep learning workloads. So for data processing, we can use Intel Modin, which is a drop-in replacement for Pandas, meaning you can accelerate processing without having to change API code, and it works especially best on Intel hardware. For feature engineering and model training, we can use Intel extension for PyTorch, which extends PyTorch with optimizations for extra performance boost on Intel hardware. And most of the optimizations will be included in stock PyTorch releases eventually. And the intention of the extension is to deliver up-to-date features and optimizations. Now, before I move on, Intel 1DNN optimization for TensorFlow has already been integrated with stock TensorFlow for back-end CPU optimization. And it's automatically enabled for TensorFlow versions 2.9 and above. And that's ultimately the goal we're trying to achieve with PyTorch and these other frameworks. For hyperparameter optimization, we use SIGOPT here to optimize our model. It provides a simple API for hyperparameter optimization and allows us to achieve high performance gains with better accuracy. For quantization, we can use Intel Neural Compressor to quantize our model. We use an accuracy-aware quantization technique to dramatically reduce the size of the model and computational costs, while also monitoring for potential accuracy losses due to changes in precision. And lastly, for inferencing, we can use OpenVINO, which stands for Open Visual Inference and Neural Network Optimization, for optimizing and deploying AI inference deep learning models. Now, you might have some questions regarding the reference kits, such as what is the use case and the proposed solution, how do I implement the solution, and how do I achieve the best performance, and can it really accelerate my workloads? Now, each of the reference kits includes a solution brief, the developer guide, the code repository, platform architecture, as well as benchmarking results for before and after optimization. We provide plenty of information to developers to further customize and fine-tune their models with data from their industries. In the next slide, we can take a brief look at one example from the reference kit and discuss implementation and the expected performance boosts. So here we have an example of one reference kit. We have that uses an SVC model from scikit-learn for document indexing. The only change you have to make in your script is just adding a couple lines of code to enable the optimization. As you can see from the screenshot on the left, the upper box has the optimized packages while the lower box has the stock packages. And the only difference is that for the optimized version, we use Modin instead of stock pandas, and we use scikit-learn extension instead of stock scikit-learn. Now, with only these changes made, you can seamlessly speed up your scikit-learn applications. In this example, we are seeing around 2.5x boost in data processing performance, 25x boost for your training performance, and almost 2x boost for inference performance. Now, depending on your use case and complexity of your model and data set, your performance gains may vary. In addition, we're able to achieve the same level of accuracy when using Intel scikit-learn extension to optimize our model. So there is no drop in accuracy after optimization. This means, for this example, the computational savings obtained by using SVC will allow us to perform expensive hyperparameter tuning in shorter time, therefore optimizing the model in the future. What Intel has done here is provide a cost-effective way, to deploy your model without having to sacrifice accuracy and performance. I think now we have a pretty good understanding of the Intel AI toolkits and the reference kits. So we can shift over to the Jupyter Notebook for our simple demo.
Yeah, I'm really excited to see this demo and how this kind of plays out. What's the kind of tools that you'll be looking to use in this demo here?
Yeah, first, we can talk about the hardware. I'm using a bare metal instance from the Intel Developer Cloud. And the reason is because I want to be able to use the latest generation Intel CPU. The codename is Sapphire Rapids 4th generation, and it should be available on most cloud providers very soon. And in this short demo, I'll be showcasing the performance boost you can achieve from using Intel PyTorch extension, or IPEX as we call it. And we're going to focus on inference. And for performance metrics, we'll look at throughput and inference time. And then we're going to compare the stock PyTorch model to the Intel optimized model, as well as the Int8 quantized model. Additionally, we can also look at the ease of use you can get by using IPEX. All right, so like I've said before, this short demo, we want to showcase the performance boost you can achieve from using Intel PyTorch extension, or IPEX. And we're just going to focus on inference for the sake of time here. And for performance metrics, we'll look at throughput and inference time. And we're also going to compare three models, the stock model, the Intel optimized model, as well as the Int8 quantized model. And we can also look at the ease of use of using PyTorch extension as well. So we can actually begin running our notebook. So we'll be ready when we get down there. Before we get started, we'll need a few things. We'll need to install PyTorch and Intel extension for PyTorch. And then moving to the next cell, we want to just import the packages as we normally would. And for this example, we have created this inference function that we're going to call on each time we run inference for each of the models. And it's going to output the throughput as well as the inference time. Next, here we have specified the model we're going to run, the batch size, warm-up iterations, as well as the measurement iterations. We've chosen the ResNet 50 model here because the runtime, it's reasonable for this demo, and that's why. Moving on, first we're going to look at the stock PyTorch model. This is the first unoptimized model. And the first thing we're going to do is define our model and input. For our data set here, we're going to just generate random numbers to import into our model. Next, what we want to do is convert our model to channel last memory format. And this is common for vision models, and it's more favorable for performance, and that's why we do it. Next, here we just clear the caches just so that we get consistent results throughout this notebook. And then this cell here, we're going to just run the inference for each of the models. So this one should be about done, and it's going to output the throughput and the inference time so we can use it. And we'll use it as a baseline before we look at the performance of the other models.
So these baselines that you're talking about, are these basically what we would expect that other people are doing examples on as well, since it's a ResNet 50 and it's just general models that are available? So we're using pretty standard stuff here, correct?
Correct, yeah. So the relative boost and acceleration you should see between unoptimized and optimized should be pretty similar to what you're going to see today in this demo. So the first stock PyTorch model has just finished running, and we're seeing that the throughput is approximately 107 images per second, and it took about 89 seconds to do that. And we'll take a look at the Intel optimized model to see the difference in performance as well. So in order to optimize your model here, we'll just need to change the code a little bit by just adding 2 lines and only 2 lines. So first we'll define the model again as we have done before, and the data set. And then next we will convert the model to channel's last memory format as we've done before. And then here's where the change comes. So what you'll need in order to optimize your model, your stock model, is you'll need to import IPEX first. And then for implementation, you will use that to optimize your stock model here. And then once again, we clear the caches here so we get consistent results, and then we run the inference. As you can see here, the throughput is much higher than it was for stock PyTorch model, and it was done in less time. So to give you an idea, when we compared against the stock PyTorch model, the FP32 optimized model is 2.4 times faster. And so that's the kind of performance boost you can expect when you're using Intel optimizations.
So this is a great example of just saying you already have this ability basically on the Intel platform today. We just got to make sure you're using the right software and the right code, right, to get those optimizations and just leverage them.
Exactly. All right, moving on to our last model. We're going to quantize our model to an int8 data type, and we're going to use IPEX to implement that. So if you haven't already imported IPEX, you'll need that in order to quantize your model. And we'll also need a couple more packages here to prepare and convert our FP32 model to an int8 data type. And once again here, we'll import our model and input, and we'll convert the model to channel's last memory format. And then the next step is where we quantize the model. So in this first line, what we're doing is defining the quantization configuration, which is essentially the model compression technique you want to use. So in our case, we're just going to be using a static quantization. And then next, we're going to prepare the FP32 model and convert it to an int8 model here.
So Barry, now that we're here and I see this quantized model, and I'm kind of new at all of this, so can you help me understand why we would do this in the first place after you just showed me so much better performance up above?
Sure, Brian, I can answer that for you. So looking at it from a business perspective, right, inference is very important, right? It's critical for business. So when we optimize the first stock model to using Intel software optimizations, it optimized the performance without a drop in accuracy, right? And so next, we can get further improvements and acceleration by quantizing that model. And so when we do that, that could be the difference in spending a lot of money, especially for large businesses. And so when we quantize the model, we can compress it, and it's able to run a lot faster with better performance without dropping too much accuracy. And so that's very critical for businesses and to get that edge or advantage in the market.
So this is a good place that we're going to then see, I guess, is the Intel deep learning boost solutions that have this ability to run in inferencing faster.
Correct. And as I mentioned before, I'm using the latest 4th gen Intel CPU, and it's the new Sapphire Rapids architecture, which introduces AMX, which is the built-in accelerator, right? And so the AMX instructions accelerate matrix multiplication and support BF16 and int8 data types. And it's ideal for improving performance of deep learning, training, and inference on CPU. Now, we need these instructions to achieve this level of performance, and they're available on Sapphire Rapids. So moving down this notebook, once again, we're going to clear the caches so we can get consistent results. And then we run the inference on the int8 model. And here we're seeing that the throughput is significantly better. It's almost 1,600 images per second, and it completed that in a lot less time, only 6 seconds. Now, to give you an idea again, when we compare the int8 quantized model to the FP32 optimized model, the int8 is over 6 times faster. And then when we compare the int8 against the stock, the initial model, it's almost 15 times faster. And so this is the level of performance you can expect to achieve when using Intel optimizations as well as Intel software to quantize your model.
This is great. I mean, Barry, what you're really showing me here is, boy, get the latest Intel gear that you can, or keep what you have, and definitely accelerate it with just leveraging a couple switches in software code.
Exactly. Intel has designed this to be very easy to use for its developers, and so anyone can use it. The first step you can take is to go on our GitHub and rerun those tests yourself, where the instructions are easy to follow.
Everyone, I really appreciate your time listening to this session today. Just remember, please check out our My Build Intel Feature Partners page. Check out intel.com for additional information. We have all the social media outlets that you would expect: LinkedIn, Facebook, YouTube, Twitter. And of course, please dive in and check out all the good stuff that we have for demos and content at GitHub. This will be a good place for your resources to get you started.